Um, I now begin chapter 5 of my course, which is the last chapter I intend to include in my linear algebra course. And it is on eigenvalues and eigenvectors and diagonalization. But I want to start with a little motivation for eigenvalues, why we might even be interested in them. And let's start with linear differential equations with constant coefficients. This is a simple first order such equation. Put it in this format. And we're not, of course, x just equals 0 is a solution, right? It's a trivial solution, and we're not really interested in that. We want all the other solutions, the non-zero solutions. One method for doing that is to assume, and here x is a function of t, is to assume that x has this form, some constant times e to the lambda t. And we want to find lambda. Well, so if this is what our x is, this is what dx dt is. It just bring down the lambda, plug it into the equation. Here's the equation. Oh, what are we? Here's the equation. Plug that solution in there. And you see this all works out if lambda equals a. So that's our solution. Lambda equals a. So here's our solution. X equals some constant times e to the at. Simple enough. What if you got more than one equation and more than one variable? Here there's two differential equations and two variables. So we do the same kind of thing. We assume solutions of these forms. I'm hoping my computer works. It seems to be a little glitchy. Plug them into those equations up here. I can divide out e to the lambda t. It's never going to be 0, right? So I'm left with these two scalar equations. Put them in matrix format. And what I have is this equation. This equation is called the eigenvalue problem. A is a square matrix, K is a column vector, and lambda is a scalar. Remember AK, anything in A's column space could be on the right side, right? That's what the column space means. But we're only interested in these things which mean parallel to K. We want AK to be parallel to K itself, geometrically. Anyway, let's look at that eigenvalue problem. A can't be 0. Here's what all the sizes are. Let's take this equation and do a little matrix algebra with it. Let's move it all to the left side. And I can multiply by the identity, right? That way I can group these things a little different. I can say a minus lambda I here. And let's stop on this equation for just a second. It is a homogeneous equation, a 0 on the right, with the unknowns being the elements of this column vector K. Well, from previous work on how to characterize solutions, you know, one of two things can happen. Either there's exactly one solution for K, and if there's only one, it is the trivial solution, meaning K equals 0, and we don't want that. So it leaves the other possibility, which is you have an infinite number of solutions for K. And what are the conditions on this upfront matrix here, this A minus lambda I, so that you get those infinite solutions? Well, if the determinant of this matrix is not equal to 0, you'll get the unique solution. So we want the other case. We want this determinant to equal 0. And that's how we're going to find the lambdas. We want to find all the lambdas such that this statement is true. I'll save the example for the next video. that is the eigenvalue problem.